Alright, last time we'd got as far as a player that can move around and shoot stuff and faces the direction they're moving and indeed fires in the direction they're moving, which is cool. This time we're going to add physics to this, which is surprisingly easy in Unity. It's one of the nice things it mostly does for you. But before we do, I need to clarify something that I've been doing slightly wrong. I'm using a different code editor to you, or a different version of the code editor. This is Visual Studio 2019 Community. If you downloaded Unity by the link I provided, you probably got Visual Studio 2017 with it. It is unbelievably hard to make Unity give me that version. I want that version. I want to be using just whatever it comes with. I could not make it happen. Now that I know from you guys what version it is, I still can't get it. For reasons, it is so complicated. It would be the entire lesson if I tried to explain the journey of me trying to get the right version. I can't. I just can't. So I'm going to carry on using Visual Studio 2019. If it's not going to be... I don't believe there'll be any actual real differences, like things I'm doing that you can't do. If you do see anything like that, obviously tell me, but I'm pretty sure that won't come up. The most visible difference is that I think Visual Studio 2019 is doing some highlighting of these words, like making things different colors that are actually all the same color on 2017. If you really like that and that's very useful for you, you could go and get Visual Studio 2019 Community. But I'm not going to recommend that necessarily because it's just a bunch of extra hassle for a very small improvement. And hopefully just the fact that it's different on my screen might be helpful for you. Just as I'm explaining it, you'll be able to see that these different terms are different in some ways. Like, you know, get axis is the same color as look at here. I mean, I don't really know why. I can't say that this makes immediate sense to me. But certain things like... no, really, I was looking for any consistent pattern here and I'm not really seeing it. So don't worry too much about the colors. All right. Also, I've fixed a potential problem. No one mentioned this, but I was noticing my cursor was very hard to see on the dark background because for some reason it comes out differently in the video than it does on me. Now it's highlighted. Hopefully you can see that little yellow highlight. And then another little bit of catch up is this chunk of code here. That's our movement code. We rewrote this to make sure that you knew where you're going before you go there, so that you can face that direction. A couple of people found this was the hardest part to follow so far. Nobody said they didn't get it, but all the same, I'd like to just go through it one more time just to make sure everyone's clear on what we're doing and why. This actual code is not going to last very long. We'll change it even in this episode, but I just want to make sure you understand the process that we went through and the terms we used, because we might as well introduce them as soon as they're used. So, the key thing really is this input vector. So this is us going, we call the input hotline 2 different times in this line of code, and we ask it for what's the horizontal axis doing, what's the vertical axis doing. And from that information, we make a vector. And so that's why there's the word new here. We don't have a vector yet. When we added vector3.forward to some stuff, that's a pre-made vector that already exists. The vector hotline has that ready for us. Here, there is no existing vector for what the input is doing. That's a very custom thing that we're creating. And all we have is some numbers. We have 3 numbers. We have what the horizontal axis is doing, 0, and what the vertical axis is doing. 0 is the y coordinate because we don't want to go up or down. And to build a vector out of 3 numbers, you have to basically say to the vector hotline, hey, can you build me a vector out of this? I want a new vector. Let's make a new vector out of these component parts. And then the next thing we do is from that vector tells us what the input is doing, what the player is trying to do, and then we multiply by max distance to move, because we can't necessarily move as far as you know, 1, 1, whatever that would represent in space. We don't necessarily move a meter every update. We need to scale it down by both whatever the player speed is set to and this time.delta time thing, which just factors in how fast the game is running. If the game's running a lot of these updates, let's move less per update so that we get a consistent overall speed. And then new position is just, okay, given that this movement vector is how far we're going to move, add that onto our position. And I've also got a little drawing app now that I can do diagrams on them. So partly to test this out, I'll just try and visually represent what's going on here. So remember the input stuff, we're using WASD. It could equally be, if you had a gamepad plugged in, it could be a thumbstick. So let's say you're using a gamepad thumbstick and you're pushing it all the way to the top left. This is a thumbstick being pushed to the top left. What we're doing here is building a vector out of, there's a vertical component to this, like that, and there's a horizontal component to this, like that. Those are 2 numbers, and we build those into a vector that is basically v, comma 0, comma h. Actually, it's the other way around. Let's get this right. H, horizontal first, 0, v. That's the vector we build out of it. But what that really amounts to is an arrow, a sort of a movement that goes, like, in this case, if we're pushing the thumbstick up and to the left, this movement that we have is it's up and to the left. So that is what, let me switch back to this. That's what this line of code is doing. And now the next one is just scaling that down to match the speed and the distance we can move this frame. So all we do is it's same direction, but now we want a slightly smaller arrow that is how far we can actually move this update. That's what that line is doing. And then new position is we're taking our transform position, our current one, which is just a spot in space here, position P, and we add that little smaller yellow arrow on to arrive at a new position, NP. Writing, not my strong point here. Let's take another go at that P. I would have to pay for this app if I wanted to be able to type letters, and I'm not going to. So yeah, we've moved in space. So we're starting from a certain position, we arrive at this new position, and now that we have that new position, we can both move there and look there as well. I don't know, if none of that helped, oh yeah, let me just finish this by underscoring that. That's what that line of code is doing. If none of that made any visual side of it and it made any sense to you, don't worry, as long as you basically have a rough idea of what we're doing here. Okay, let's wipe all that and let's get on with some physics. The reason we want physics, well, first let's mess around with our scene here. So go to the scene view here in Unity. The kinds of behavior I want to add is things like bullets bouncing off walls, and just bullets being a physical object in the world, and maybe bullets won't be a primary kind of thing we want bouncing around, but we all want some physics stuff, and it's fun to mess around with. So we're going to add it. But for bullets to bounce off walls, first we need some walls. So I want to add some more things like this ground object, but higher up, in a wall type shape surrounding this area. We could create those by this menu the same way we created everything else, but actually I'm going to just right-click the ground and duplicate it, because that way it will have the same material already, it will look the same, some of its dimensions are right, and you can use this rectangle tool to scale it to be, right now it's right where the original ground is, but actually we want to extend it vertically, which I'm having a little bit of trouble doing. I'm just going to use these values over here. Let's make it like 3 tall and maybe 3 deep as well, and then 20 for that dimension is fine because we want it to run the length of the arena, and then its position is a little bit off. Let's go to this move tool where we can drag things around. If you hold down control when you're doing this, it'll move in whole steps, so that's kind of handy to get things to line up exactly. Or it would be in theory. Doesn't seem like that's going to happen. What if I'm just going to kind of fudge the figures here so that the maths is easier for aligning. I think that's right, isn't it? Yeah, so those are perfectly flush now. The height, I think, also is. Let's see. Oh no, I know what I want to do. Okay, so yeah, you can futz around with those values just with moving and dragging things. It's ended up, for me, it's being 23 and 2. And I've just picked scale amounts such that the coordinates are nice whole numbers. If you want to change these to whatever you like, you can do that, but then the coordinates will be slightly more fussy. It'll be like 1.5 and minus 0.5 and things like that. I'm going to duplicate that now, and now that I've done that, I should be able to drag it across the other side. I need to move the camera a bit to check I'm doing it the right way, but yeah, that's nice and flush. And then we'll do it again. At this point you could rotate it, I guess. Should we try that? Yeah, that works, kind of. And as long as that lines up nicely... Oh, actually, we're going to do this slightly differently because we've got these nasty corners things here. I think to fix that, I'm just going to type in 24 there and have that cover it. And now when we duplicate this one, it's going to be very easy to finish off our arena. It's going to go something like that. All right, we've got an arena, but when we play, we're going to find that in our current world, walls mean nothing. You can walk straight through them, you can shoot straight through them. They are immaterial. So this is a problem we were going to hit, right? Even if we didn't want barriers at the edge of our level necessarily, if you want to put some cover or any kind of obstacle, we're going to find it doesn't do anything yet. That's because our game doesn't have any physics in it. We could hand code our own physics, but luckily Unity has its own sense of physics, and we can just use that. Everything we've built, all these ground objects, and in fact even the player and bullets and stuff, they all come with a component called a collider, which you could be forgiven for thinking that's going to handle collision for us. It is going to be used in collision, but nothing, if you actually want physics to simulate things, if you actually want a collision to do something, to stop, and just behave in kind of the natural way you'd expect solid objects to behave, you have to make at least one of them be a rigid body. So we're going to take our bullet. So find your bullet in the project folder. It's not in our scene. And over here, let's actually click Open Prefab, because this is how we normally should be editing prefab. We've got a list of all our components. It's got this collider, but it's not doing anything yet. When I click Add Component here, I've already typed this earlier. So you're going to type rigid, and you can just type rigid body, I guess, the whole thing. Don't select the 2D one, just select the normal one with nothing on the end, because that will get us physics in 3D. And let's just try that straight off without doing anything to it. We just added a rigid body, and now when we fire bullets, something different happens. We've got, I wouldn't say this is the behavior we're hoping for, but it is kind of fascinating. It's like a tornado or something. Like there's a strong wind blowing all these things around. There's a bunch of reasons this is not behaving the way we quite want to, but I just wanted to give a sense of what a rigid body adds. Like there's some simulation going on now. So rigid body just means physics object. The reason it's the word rigid body is that when you're simulating things, there's rigid body physics and there's soft body physics. So all it's specifying is that this is a thing that's not going to bend or squish or change shape when it collides, or at least the physics system won't do that for you. It's going to be simulated as if it is a rigid thing, a rigid body. And that's almost all we're ever going to use. In this tutorial I can't imagine us getting into any more complex physics than that. I think everything's going to be a rigid body. Physics is, and that's kind of, when you talk about video game physics, that's mostly what you think of, I think, don't you? Like crates tumbling over each other and big brick walls all falling apart. If you're making like a AAA racing game, you're going to have, when the car crashes, it's going to deform, and that would be non-rigid body physics. I don't know much about non-rigid body physics. Rigid body is both the simplest to work with, and also it just runs really fast. Like this is what games are built to do, that your graphics card or your CPU is really good at doing this kind of calculation, and Unity is, has its own physics engine that is optimized to make this run well, which is going to be cool for us because we're making quite a simple game, and that means we can just have masses of stuff going on and it won't run really slowly. So why is our bullet behaving in several weird ways? There's a few things. One is right now we're creating the bullets. Let's go back to our player behavior. When we click fire, we create a bullet prefab at our position, transform rotation. And let's just see what that would be like. What are we doing? In scene view, I'm going to go over to our player, and let's just drag a bullet from the project folder just into the scene. I'm just going to dump it loose in the scene here. And is our player at 0, 0, 0? Not quite. Let's put our player at 0, 0, 0, and then let's put our bullet at 0, 0, 0, and see what we get. Oh, really? Okay, no, our player is not at 0, 0, 0. Our player is at 0, 1, 0, correction, because the ground is 0, 0, 0, so we went one up from that, didn't we? The point I'm trying to make is the bullet is inside the player when it spawns, and then it's trying to pop out. And like I say, all this stuff we built already has a collider, which means things can collide with it. And when something is a rigid body, that means it'll actually look for that and react to it. So right now, although the player doesn't have a rigid body yet, the bullet does, and that means it looks for colliders and it bounces off them. And it starts inside one, so we've given it a kind of impossible job. It's like, well, what the hell do I do with this? So let's what we could do in future, once we have like a player model with a bunch of components to it, and it looks like whatever we want to look like, we could have a sort of a specific spot on that model that we designate as here's where bullets should spawn. But for now, we're just prototyping. We're just trying to make things fast. I'm going to delete this. Actually, let's test. What if this bullet was 1 unit ahead? So it's at 0, 1, 1. That would be fine, wouldn't it? That's outside of the player, clearly. It's close enough that you're not going to miss stuff. I guess if you wanted to be really fancy about it, you could sort of drag it and then find this exact coordinate. I'm not going to do that because the actual size and shape of our bullet might change anyway. So this is just a sort of a quick hack to fix this one problem, which is instead of spawning at our exact position, let's just add a bit onto it. Now, the term we're going to write here is one we've already encountered. It's not vector3.forward, because that would be the absolute forward, which is basically north. We don't want them to always appear north of us. We want it to be relative to us, right? And that is transform.forward. That's the same term we used on the bullet to get it, to figure out which direction its speed should be in. And I'm not multiplying it by any other value or anything. I'm not saying how far in the transform forward direction, because the default value is 1. Transform.forward is 1 meter in the forward direction. And that, as I just demonstrated, it's enough. It might be slightly too much, but we can fix that if that becomes a problem. For now, we're just going to make sure that these things don't spawn inside us. And before we test, I'm going to delete this bullet, because I don't like having having a bullet already in the scene is a weird thing. Okay, so now they do at least fire directly out of us. I told you they would bounce off these walls. They're not really bouncing off these walls, are they? I think there will be a bunch of potential fixes for that. So the reason that is happening is this bullet behavior that we wrote, we manually modify the position of the thing. This is a very we're really reaching into the guts of the code and just saying, you go there. We're forcing your position to be there. No matter what the physics engineer is saying, we make you move. And so there's nothing in our code that says, oh, don't do this if there's a collision. Our code just runs all the time. So we're always going forwards. So actually, this is really us doing our own little physics simulation. We're saying, oh, that rather than tell you it's got speed, which we couldn't do because it didn't have a rigid body at the time, there's no built-in way to just sort of have these things move normally without a rigid body. So we wrote our own little speed code, which is, we've got this value bullet speed, and we're going to add it on every frame. And we did some clever stuff to make sure it ran at the right speed and stuff. But actually, if you have a rigid body, that is done for you. There is a thing called velocity, and you can just, we're going to write a line something like rigid body dot velocity equals something. It's actually going to be transform dot forward, that same thing that we just used, times bullet speed. That's the line we're going to write eventually. The reason I've written it as a comment is we can't, this thing doesn't have a reference to its own rigid body yet. You can write transform anywhere on a component because a component knows it's going to be on a game object, and every game object has a transform. All of them do. Not all of them have a rigid body. And if something might not have a component, you can't just access it directly. You can't just sort of assume it's there. Because they want you to write this code in such a way that it could be moved somewhere else and not crash. So we need to look for a component that is a rigid body. So the code for that, we want to get a reference to a component, so we're going to write get component. It's going to autocomplete. And then, weirdly, we're not going to write normal brackets here. We're going to write pointy brackets and write rigid body in there. And then we're going to do normal brackets with nothing in them and a semicolon. This is a bit weird. This isn't the full line of code yet, but just to explain this one function, because the way we're calling it is slightly strange. Just to recap functions, when we ran instantiate, this is a function, and then in brackets we put all these things are called arguments, and arguments are just details. You've got to supply some details. When you say, I want to instantiate something, the instantiate function needs you to supply some details. It needs you to supply what do you want to instantiate, where do you want it to be, what direction do you want it to face. When we ask the input hotline to get the status of a button, we had to pass in an argument. We had to give it some details. I want the state of a button. Okay, what? Like, what gives you some details about what button you want? We passed in this argument fire. And then look at, transform, look at something. Well, what do you want me to look at? New position. This one is slightly different because the thing, we are telling it in advance what type of thing we want to get back. So it's get component, and we want it to give us a rigid body back. And do you remember how we had to, if we want to declare a variable, you've got to say what type it is ahead of time? This function can return things of any type. Well, a lot of different types. Honestly, trying to make this sound logical is failing a little bit. This is just a thing you're going to get used to over time. When the argument that you're supplying is a type, you need to put it in these pointy brackets rather than normal brackets. And then actually there's nothing in the normal brackets because there's nothing further we need to supply. It knows we want a component, it knows the type is a rigid body, that's all it needs to know. I'll look for a rigid body component and give it back to you. So actually, maybe we just do it like, I'm trying to think what the most logical way to do this is. I think we will, this is a reference, and I think we'll store it as a variable. So we're going to declare a variable, a rigid body type variable. So we type rigid body first, and I think the variable name is just going to be our rigid body equals get component rigid body. So this is just like when we said vector3 input vector equals this. It's just like when we said float speed equals this. We're saying rigid body, the thing we want to store is not a number, it's not a vector, it's a rigid body. The name we want to give it is our rigid body, and where's it going to come from? Well, please go get us a reference to our rigid body. Find a rigid body on this game object and give that back to us. And then we can type our rigid body dot velocity equals transform dot forward times bullet speed. So that says, now that we've got our rigid body, I'm just going to tell you, here's the direction and speed you're going. Velocity is just speed and direction together. It's this is the same way that word is used in physics. If you talk about a car's speed, you can say it's 60 miles an hour. But if you want to talk about a car's velocity, you've got to tell me which direction is it going 60 miles an hour. If 60 miles an hour north is a velocity. And a velocity is a vector. A speed is just a single number. And so actually what we're doing here is we're multiplying a vector by a number, which is our speed. And we are not multiplying it by time.delta time, because we're actually doing all of this in the start event. I didn't mention this when I did it, but just to say that explicitly now, we want this bullet to set its speed on startup, and then now that the rigid body has been told what velocity it is, it will continue on at that velocity until something happens. At that point, it's in the physics system's hand. We're saying, look, you are a physics object. We're telling you what velocity you've got now. From after that, it's up to you, mate. Like, if you hit something, you tell me what the velocity should be. I'm not going to tell you. And that's what we want, because previously we were forcing it to move along. Like, we are telling you your position is this, your position is this, your position is this. And the physics engine didn't have a chance to do anything about it. It's like, oh God, okay, you forced my hand, so I can't have any collisions. Now we're just saying, okay, physics system, velocity, here's the heading we're on, here's how fast we're going, up to you. So let's delete our code from update. This is going to happen at start, and let's just see how that works. Oh, by the way, just to explain something we saw earlier, you know, we had that hurricane effect with the bullets, sort of swarming around. That's because with our code that we just deleted, which I'll just get back for a second, this is always moving in the direction of our transform forward, which, as I said, is relative. So if it gets bumped by the physics system, it's still going to go in the direction it's facing. So it's almost like a homing missile, or not a homing missile, or just a missile, where it's being propelled from behind all the time. So if it starts to move a little bit that way, it's going to go a lot that way. And that's why you got that swarming effect. I just thought that was kind of interesting. But let's delay no longer and see if our code works. Yes, look at that. They are bouncing off the walls beautifully. They can go through the walls if I go through the walls, because understandably, I'm still not a physics object, so I can just walk wherever I want. But when we shoot them into the walls, they're piling up nicely. And it's really fun just to see physics objects stack up. Like this number of things, there was a time when it would have blown my mind that you can just have all this running and it's not slowing the game down to a crazy extent. In general, you don't want, I mean, be careful with physics. Don't commit to a game design that involves billions of objects all stacking around like this, because it will perform differently on different people's computers. But with our basic little game, this many objects is going super smooth. So yeah, Unity is doing all this work for you. Like to code that behavior, have all these things bounce off each other just the way real physical objects would, I just wouldn't know where to start. It's absurdly complex. We coded some sort of rudimentary physics for heat signature, where it's a 2D top-down game without spaceships, and when the spaceships collide, they can bounce off each other in certain ways, and we did that ourselves. And that was a very basic version of it. And yeah, so it's cool that we get all this for free, basically. So the player can still walk through walls, though, which is not so great. So we should give the player a rigid body, I think. And that's as simple as going to player and add component and rigid body. Let's see what that does by itself. Okay, the walls do sort of stop us, he says, walking through a wall. But as you saw, when I was bumping up against the wall, that was kind of a nasty look, wasn't it? That doesn't look like a game functioning correctly, or something's going a bit screwy there. And so that is the exact same problem that we just fixed on the bullet, which is that we now have two different systems for motion. We've got a rigid body, which is going to react to colliders and let this thing bounce off stuff. But our code is again doing this brute force thing, and we just change your position. Transform position equals new position. I don't care what the physics system is doing, we're going to move you there. And so what's happening when you're moving into that wall is our code is saying, move into the wall, like you're in this position, don't care if there's anything in the way. And the physics system, once you're in there, is saying like, God, two things have collided that aren't allowed to collide. These are both rigid bodies, they're not allowed to be inside each other. Pop it back out. And the reason I went all the way through the wall at some point was that, whether or not you end up, that initial like digging in, that sort of embedding that you do, whether that takes you all the way through the wall is down to chance, really. It's even down to like how often the update thing is running, which is terrible. But now we have a rigid body, so we can fix that. And in this case, let's do it in... I'm just thinking we would need a reference to our rigid body. I guess let's do it the same way we did in bullet behavior. So then we can just copy and paste our code. So we're going to take our rigid body. Let's do it. Let's just do it right up here, because our new code will, after we've done this, we won't need a bunch of this other stuff. So again, we're going to declare a variable type rigid body. We're going to call it our rigid body. And what is it going to be? Well, we're going to ask Unity, hey, can you get me a reference to a component? The type is a rigid body. That's all I'm telling you. If there is one, give it back to me. We know there will be. So we're just going to use it. Now, what should the rigid body velocity be? Dot velocity equals. It's going to involve this input vector. We want to care which way the thing is going. And it's actually much like, if you remember what we did with our bullet code, it's a bit like the old code, and we're not multiplying by time.delta time anymore. So we want the input vector multiplied by the speed. So max distance to move is speed and time.delta time. We don't want time.delta time anymore because the physics system is going to handle that for us. We are, of course, hitting a problem where input vector has not been defined yet. We need to define that up top. So sure, let's do it there. So we get the input vector, we get our rigid body, and then our rigid body velocity is our input vector times our speed. Speed, actually, really speed is max speed, isn't it? And when we set that speed, we don't mean you're moving at that speed all the time. That's the fastest you can move, and it's in meters per second, which is going to be how the physics system interprets it as well. And yeah, so if this input vector was only half a unit long, then we're going to move at half speed. And let me think, is that all we need? So we still want to look in the position we're heading, so we need some of this other code, but we don't need all of it anymore. In particular, max distance to move doesn't matter anymore, because it's going to be the physics system that decides how far we move. We're just telling it, here's your velocity in meters per second, you take it from here. And that means that the movement vector, we don't need that exactly anymore. We need something like it, but not quite that. And that means new position. We don't want to use that. Right, this is the actual offending line of code, isn't it? This is the one that's making us go through walls. Its transform position is moving to new position. Well, we don't want that. Physics system is going to handle that now. But we do want to look in the direction we're heading. And right now, that used to be the exact position we're going to move to. We don't know that anymore, because now the physics system is going to handle it. We don't know if we're going into a wall or not. And we don't need to, because which direction you look doesn't depend on whether you're going to hit a wall, because we're a video game player. We walk face first into walls. That's one of our defining traits. So all we really need is just, it's still going to be transform position plus something, but it doesn't have to be movement vector that's carefully judged, like here's how far we're going to move this frame, and it depends on the rate time is flowing and all this other stuff. We can just do that plus input vector. Because, input vector. Because input vector is going in the right direction at least. Its length is kind of arbitrary at this point. It doesn't necessarily represent how far we're going to go, but we don't care how far we're going to go. We just want to know the direction. And as long as, since this is just a position we're going to look at, we don't care if it's further away than the position we'll actually end up moving to this step. All we care about is what direction we're facing. The direction we're facing is the direction we're moving, the direction we're trying to move. And in fact, even if we were like trying to move into a wall and we had some physical reaction where it bumps us out and technically we're moving backwards, even in that scenario, we still want to face the direction the player's trying to move. It just kind of looks right to do that. So that is still what we want to write. I think maybe we shouldn't call it new position anymore. So I'm going to right click on this and say rename. You can do this with variables, and I'll call it look at position, just to remind us this isn't necessarily the position we're going to, it's just the position we're going to look at. The position we're going to look at. That renaming thing is super useful, but one quick caution on that. If I rename speed here, I was saying this probably should be called maximum speed, but if you rename a public variable that's set in the inspector like this, that data right now is just being held in the inspector, and if you snatch that name from under it and change it to something else, it loses that data. So be careful about renaming public variables that are set in there. There's a way around that, but it's beyond the scope of this tutorial. We don't need to get into that because we're just not going to do it. Avoid it by not doing it. So let's just slightly shuffle this stuff around just to make it look a bit nicer. Okay, get an input vector, get our rigid body, set our rigid body's velocity. Then face a new position. Okay, find a position in that right direction and look at it. And that should all be correct now. Yeah, look at that. Wonderfully smooth. Yeah, we are pretty much done adding physics to our game. There was one thing I had in back in my head to add at the end of this, which is, yes, there's still another way it could go wrong. It isn't, we don't have this problem yet, but just because you might experience it and not know what the hell is going on, for the sake of experiment, I'm going to try making one of these walls very thin. And now, you might have noticed for just a second there, some bullets went through it. I partly made these walls thick so we wouldn't hit this problem at the same time as the other problem, because the two problems look just alike, don't they? Like the first problem we had was we were going through walls because our movement code was just brute force. It was just change the position no matter what. That's one problem. We fixed that, and it was working fine, but now with thin walls, we're going through them sometimes. This is a problem called tunneling. It's a very common problem. You'll see it in some professional games because it's happening because even in the physics system, our bullets are moving super fast and it is still running in updates, even though our code is not in the update loop for the bullet. Still, the rigid body velocity thing it's doing a certain number of updates per second, and in one update, it hasn't hit the wall yet. And in the next update, because it's moving so fast, the amount it's moved by, it's on the other side of the wall, and so it still also isn't hitting the wall. In neither case is it hitting the wall. So it ends up going through it. Obviously, we don't want that, and there is actually a way to avoid it. So on our bullet, open the prefab. Under its rigid body, there's this collision detection field, and it says discrete. If we change that to continuous, there's two other options there that I don't 100% know what the meaning of all of them is. Now we have solved the problem. So why aren't they just continuous by default? Why isn't that just how everything works? Well, it's just slower. It just takes up more processor time, because this is a bit of a layman's guess at how all this is working, but I believe when it's discrete, what that means is it's happening in discrete steps. We're just checking, have you collided in this step? No. Have you collided in this step? No, you're all fine. Let you through. Continuous, I believe, is looking, checking every potential spot between here and there. It's doing a what's called a ray cast, where you look ahead to see, would I hit it there? 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 And only if all the positions are clear, do you actually go there. I'm pretty sure it's not literally doing that many checks. It's probably have some clever maths to make that run faster, but it is overall slower than doing the discrete thing. The discrete thing is the simplest possible thing. So if you had like a huge number of objects that are never going to hit a thin barrier, let's think of a metaphor for that. If you're in the Minotaur's labyrinth and you're throwing beach balls around, you're probably not going to have any tunneling problems because the walls are nice and thick. Things aren't moving crazy fast compared to their size, and if you wanted 1 billion beach balls in the Minotaur's labyrinth, to be honest, a game that sounds quite good, you're fine with discrete because tunneling is not going to be an issue. In our game, I can envision there being some thin barriers and some fast-moving objects, so let's leave it on continuous. Continuous is good. We don't need to solve the performance problem unless we actually have a performance problem. That's my philosophy. Some programmers would strongly disagree. I'm just going to get that back to where it was now. Oh wait, this was too thick, wasn't it? And I'm not going to rotate it. There we go. All right, so that is fixed. Physics, so that's the lesson, that's over. Messing around with physics, lots of things could work here. What if... One thing I noticed as I was playing around was that the bullets can affect me a little bit. And in fact, if I push into them... oh, here we go. Oh, look at that. Look at that. I'm hovering. And I'm spinning. So this is a problem that we're hitting because the physics engine is allowed to... whoa, I'm spinning in 3D space now. Did I stop? No. So it might have looked like we were walking along the ground, but we weren't. We were just a body that can move freely, except that we are manually setting the velocity. So while we're manually setting the velocity, it should be pretty consistent, but when we stop, it can kind of move freely. I'm curious what would happen. What I really want to try is, like, can we fire our bullets down? And I guess we could, to test that, actually, while I think of it, before we do anything else, I'm going to back up my project folder, because after every episode we do the mess around. I've left my project folder in a terrible state, and then I have to undo all those changes before I make the file that I'm going to upload for reference. But is there just transform down? Did that work? No. Is there transform up? There is. Okay, so we could have bullets shoot up, but we don't want that exactly. So let's go up, but multiplied by -1, which is, as I like to call it, down. Don't care about that. So this isn't going to create bullets beneath us yet. It's still going to create them ahead of us, but they're going to be shooting downwards. And I'm curious how that works. Oh, yep. We are going on top of them. And because they have no real forward velocity, they're just kind of amassing beneath us. And now we're spinning, yes. We're shooting them up into the air in a wild frenzy. That is fun. There's a way to fix this, and we'll probably cover that in an actual lesson, because it's, you know, the purpose of the screw around session is not to fix things. Let's get rid of that thing where we actually offset them ahead of us. We could offset them below us. I don't think we need to, though. I think probably just shooting them down will have the desired effect. Oh wow. Oh dear. It doesn't like that at all, does it? I guess they're not pointing down, so they're actually hitting it like side on. Man, it's really struggling with that. We could also, what if when we fire, we just affect our rigid body? We could just actually give it some velocity. So rather than, if you just do equals, you're setting the velocity, but maybe we want to increase the velocity by vector3.up times some small value, 0.1 f. F is because whenever you write a decimal, you've got to specify that you still mean a floating point value for some reason. I don't know if this is going to work. I haven't tried this. No, it doesn't work. It doesn't work at all. I think our rigid body has gravity on it. I'm not 100% understanding why the gravity, like, why we float in situations like this. Are we falling just very slowly? Yes, very slowly, very slowly. And oh, okay, I know what it is. I know what's happening. It's because we're setting our velocity, we're setting the rigid body velocity to match our input vector at all times. If we're not pressing any keys, that input vector is 0. It's nothing. So all the time that gravity is trying to push us, our movement code is overriding it and saying stay still. So actually, this might be a good thing we just add to our project in general, but for now it's just a test. Let's first check if the input vector even has any kind of input. So I'm going to write, if input vector dot magnitude is greater than 0, then we want to set the velocity. But if it's not, then we should do nothing to the velocity and let it take its own course. Yep, that has an effect. Are we going to land in the right place? Look at that! Trick shot. So this will still have some strange effects where, like, I can stop myself from falling by moving around. I can fling myself into space. Let's see what happens if instead of doing that we just we always do it, but we're adding the speed instead of setting it, and that way we won't interfere with what it's doing by default, but I expect we will accelerate out of control because it's, yep. There we go. I'm gone now. Let's see. Oh god, we're still moving. Technically I'm focused on the player here, but I just can't see us anymore. Yeah, I don't know where we are now. Oh, what are its coordinates? It's a lot in the y coordinate, it's a lot in the z coordinate. We've gone a long distance. So that's probably too much. We could add force. We do that. And now we're not talking about speed really, but we'll do it anyway. Let's see if that works. So like the truest way to do physics is to just only ever add forces and never set velocities directly, because that's in real life, things only move when forces are applied to them, and there's a friction is fighting that, and air resistance is fighting that, and that's why things don't speed out of control. If you try this, you'll feel that it's strange. It's very sluggish. If you're already moving one direction, it's going to take a lot of effort to get you back to move the other direction. It's being very physically simulated. This might be counterintuitive, is kind of the other end of the spectrum to responsive. Most action games, if people want the controls to feel responsive, that's a compliment. You say controls are responsive when you like them. And if they're true physically simulated, they usually don't feel responsive, because adding forces and overcoming friction and making things happen in a simulated way is a very slow and drudgy business. I expect if you really modeled, how games have a dash move often, like Ori and Will of the Wisps has an amazing dash move. I expect the speed you're actually moving, to affect that, to move a body with that weight from rest to the speed it moves, the force that would take could crush mountains. So game physics are extremely unrealistic, and you usually don't want to simulate it in such a real way. We'll see what kind of balance we arrive at with this. Every time I've messed with physics, I've always had to have some kind of compromise between, okay, we're not going to do true force-based physics, but we're also not going to manually edit your position. We're going to do something in between where we set your velocity, or we try and combine it there. But this is what we have for now. One more thing I wanted to try around is what happens if we add rigid bodies to the walls? Can we do that? I think I know one immediate thing that's going to go wrong, but after that, we shall see if we can fix that. Yep, they fall. Because by default, rigid bodies are affected by gravity. But there's a fix for that, right? Because we could just, if we make our floor, we can just drop that a bit and make it a bit bigger. Let's make it 24 in both dimensions. Our floor still doesn't have a rigid body on it, it's only the walls. Now the walls fall down and they land there. And what I'm curious about, we can knock them off. I'm gonna change the bullet code back to what it was. This is just what we had before. We're not going to try and propel ourselves into space anymore, and the bullets themselves are going to go forward rather than up, because I want to shoot these walls. That's what I want to do. Our bullets now propel us as well for some reason. I think I must still have some weird code in there, because they are. I think they're colliding with us maybe, or hitting the ground, or they're going in a strange direction, and so are we. We're destroying our level in the process. But you can see how immediately satisfying that is. Like, just building things out of physics objects and then knocking them down is super cool. And we might get into that in our main project as well.